A little bit about myself. My name is Dvir Yitzchaki. I work for Roku. We make televisions and streamers and cool stuff. And I recently moved to Manchester, UK, which is a very nice place. See people still taking photos. So let's give it another minute. So in CPPCon of 2015, Eric Nibler first presented ranges to the community in this talk. Anyone seen this talk, been there personally or on YouTube? So a few people. I highly recommend this talk. I personally was in awe after seeing this talk. I mean, the simplicity and the elegance of code written using ranges is simply stunning to me. And in this talk, Eric used this calendar example to show how to use ranges, basically. Now, back then, ranges were still not part of the standard library, of course, but only in Eric's library, range v3. But actually now, with C++23, we can implement the same software producing calendars using standard C++, and that's exactly what we're going to do today. First, for anyone who's not 100% familiar with ranges, we'll do a small recap. Now, what is a range? It's just a sequence of elements between two locations, I and k in this example. And we often talk about the half-open range, so k is not included. Now, a famous quote by Eric says that to develop concepts which are simply constraints on types, we don't actually look at the types, but on the algorithms that use those types. So let's do that and start with maybe the most simple algorithm in the standard library, for each. This is a conforming implementation of C++17 for each, which I copy-pasted from CPP reference. And what it does is iterate over a source sequence, and it receives a function, and it calls this function on each element, right? I assume all of you are familiar with that. Now, let's dive a little deeper. So we have the first argument, which is called first. What for each does with this argument is dereferencing it to get the values and incrementing it to advance the iteration. Pretty simple, right? So those two operations give us the most basic concept called input or output iterator. And that is any type which can be dereferenced and incremented. The reason it is not simply called an iterator is because C++ already had STD Generator when this was standardized. And adding other capabilities and operations give us more types of iterators. For example, a bidirectional iterator can go back by decrementing it. C++20 also introduced a new type of iterator which we hadn't before, and that is contiguous iterator, which tells us that all the elements are contiguous in memory and enables us more optimizations when we know that's the case. So that's the first argument. The second argument for each is called last, and this is simply the end of the sequence. And the only thing that for each is doing with this last is comparing it to first to know when to stop iterating. And this gives us the second concept, which is called Sentinel, which is simply a semi-regular type, semi-regular meaning default constructible and copyable, that we can compare to an iterator. So a Sentinel is always tied to some iterator type. And if this comparison returned false, we know that we haven't reached the end of the sequence, and so we can increment and move on the sequence. And combining these two concepts, we get the concept of a range. So a range is simply something that you can call begin to get an iterator to, and end to get the Sentinel. And the range is simply all the elements in between. So if we increment I repeatedly until we get some iterator j that compares equal to the Sentinel, then this j is the end iterator. It's not exactly the same as the Sentinel, right? So it's a bit tricky then. Okay. So for any type of iterator, we get the type of a range whose iterator has the same category. So we have input, output, etc., bidirectional, and you can see here examples of all the different containers in the standard library and what concept they satisfy. Another important concept is common range, which is this is a range whose Sentinel is in fact the same type as the iterator. For example, all those containers have that property, and if you have a common range, you can pass it to a legacy code that usually accepted an iterator pair, as we've seen with the STD for each in the C++ 17 version. But starting from C++ 20, we have additional signatures for each algorithm, which now accept either an iterator or a Sentinel pair or just a whole range. Yeah, so those are the first arguments. I won't go over the other stuff like projection and stuff like that. I had a previous talk where I delved into that from CPPCon 2019, if you're interested. But another important change that range introduced is a different return type for some of the algorithms. And that's because this law from Alexander Stepanov, which says that if a function computes some value that it is maybe important for the caller, which the caller didn't have before, then it should return it to the caller. And so going back to this definition, as we said, J here is the end iterator, which the caller, didn't have before. We only got to it after incrementing and going over all the sequence. So it would be useful to return this iterator, this end iterator, from an algorithm which traverses the range. And this, in fact, what the C++ 20 for each does. So it returns this struct, which has the function, which is what the previous version returned, as well as the end iterator, which is called in for some reason. I'm not sure why. By the way, if you don't know what no unique address is, Tim O'Doul gave a presentation about all the standard attributes yesterday. So if you missed that, be sure to check out the recording. All right, so there's a special type of range that is called a view. And that is a lightweight handle to another range. So this is a range that we can pass, since it's lightweight, we can pass it freely between functions. And you can see some examples here. If we have a range which is simply a pair of iterators, then passing it is only passing 2 pointers, basically. So this is pretty lightweight. Or if it holds its elements using a shed pointer, then we only need to increment the counter when we pass it. Or if it doesn't have any elements, actually it just generates them on the fly when we iterate through it. And we'll see examples for that as well. Then again, there's no state to pass, so it is considered a view. One of the examples from the standard library, this is maybe the most basic view, which is an empty view, whose end is always equal to its begin. So it has a size of 0. And also some other useful functions. Now, usually, we won't use the view types directly. What we will use is what's called factories and adapters. So those are objects, they're not types, which we use to generate views, basically. So if we take some range and adapt it in some way, this is called an adapter. Otherwise, this is called a factory. So in this example, we have those adapters are in the views namespace, unlike the view types, which are in the ranges namespace. And here we use the empty factory to generate an empty view of type of ints. And then we call the empty function to verify that it is indeed empty. And this is done in compile time, because everything is const expr here. All right. So if before ranges, if we would use the STL, this would look something like this. In this code, we calculate the sum of the squares of the numbers from 0 to a given count. So as you can see, besides calling begin and end repeatedly, the code is not composable. We need to have each computation in its own statement. This changed with ranges because the fact that the algorithms now can accept a single range means we can pass the range to them directly. And so we can compose it like this using the function call syntax. The problem with that is that to understand the code, we need to read it from inside out. So first we do a iota to get all the numbers, then transform to get the squares, then accumulate to do the sum. So that's a bit awkward. And for that we have the pipe operator, which enables us to read it from top to bottom and make it much more readable. Now, the pipe operator only works for adapters, not for algorithms like accumulate. So in this case, we still need to call it separately. Although we could still inline the pipeline into the last line, but I think that would be a bit less readable. Now, I lied a little bit here because C++20 didn't have a rangified version of accumulate. So this code actually uses range v3. By the way, all the code examples you see here compile and even tested. So yeah. So as I said, C++20 accumulate doesn't have a rangified version, but as we'll see later on, I hope this also changed in C++23. All right, so that was the recap. Now let's start implementing our calendar. So first we need a list of dates. Now, luckily C++20 also introduced the chrono date and time library from Howard Hinand. And now we have dates in the standard. I have this alias just to make the code a bit shorter. Instead of year, month, day, I'm simply calling it date. And so given a range of years. So the user will give us, will ask us, give me the calendar from this year to some other year. So first we generate a list of all the days using the IOTA adapter. So we get a list from all the days between the first date of the first year and the first day of the last. Because we, as I said, we look at the half open range, so we don't actually need the days of this top year. Now, date itself is not incrementable. So what we do here is we first convert it to a type called sysDays, which is simply a time point with a time point over days with a granularity of days. And then we can, this is incrementable, so we can run IOTA over it, and then we cast it back to dates. Okay, so a bit of a play here. We also want to support an infinite calendar, so the user can give us only 1 year, and then we will use the infinite version of IOTA to generate the calendars for all the years from this year on. All right, so to visualize it, let's assume we're looking at 2023. We have now a list of all the dates for this year. Any questions before we move on? Cool. So now we want to take this range of dates and start massaging it until it will look like a calendar. So maybe one of the most useful additions to C++23 is the option to format ranges using the new format library from C++20. So let's see how that looks. So now you can print, which is another C++23 addition. You now have STD println, which, as it says, print the input along with the new line. Yeah, so let's see how it goes. When we give it a vector, it will print all the elements along with the square brackets. For associative containers like set, it will print it with curly braces. We can also print tuples, which themselves are not ranges, but this is also very useful, and this is used round parentheses. And finally, for STD map, by default, it is printed as key colon value. Again, very useful and readable. Now, to customize the formatting, we have what's called format specifiers. So if in C++20 we had in the specifier an optional argument ID, which is the index of the argument you want to print, because you can print them out of order, and then followed by a colon and optionally a format spec, which is the customization you want to do, like defining the width in which you want to print, or a padding character, or hexadecimal, stuff like that. So this was for C++, basically for all types. For ranges, if we want to define the format for the elements themselves, then we add another colon followed by another format spec. So the second format spec will apply to the elements of the range. And if it is a range of ranges, then we can add more and more format specs in this way to format until the last level. So let's see an example. So again, by default, a vector is printed like this. If you just provide an empty colon, then it stays the same as the default. But if you add a format spec, then it follows it. In this example, I right align it in a 20 character width, padding it with the pound character. And then if I add another format spec, as I said, colon pound x, then this tells it to format the elements as hexadecimal numbers, along with the OX prefix. And the range format that we had before still applies, so it's still right aligned and so on. Cool. So there is more customization that was added in C++23. For example, you have a question mark which allows you to print strings escaped. So if you have a tab in the string, you will see it there. You have this M which allows you to print any pair using the colon, the key colon value as we've seen in STD map. And you have N which tells it to omit the outer delimiters. So whatever the delimiter was, square brackets, curly braces, as we've seen, it can be different. Whatever it was, it just won't print it. Okay. So we can format ranges. Now, another thing we want to do on the list of dates we got is split it to months, because we eventually want to show each month separately. And C++23 allows us to do that using what's called a windowing view. So a windowing means looking at a section of the input sequence. So the first example is chunk view. This gives you the subgroups of a certain size from your range. So in this case, for size 2, this is the result. Notice that the last range might be a bit shorter if the range ends there. We also have slide view, which is a sliding window, again of a fixed size over your element. In this case, we don't get this partial last range. It stops before that. And we also have stride view, which gives you a range of elements in constant distance between one another. So again, for stride 2, we get the first, the third, the fifth elements. Now, maybe you notice that actually all those 3 adapters are in fact specializations of a hypothetical generic algorithm with an arbitrary step, size, and whether the last range can be partial or not. Now, the paper introducing those algorithms asked whether the standard library should just provide this generic algorithm and maybe use it to implement all the others, or just provide it and let the users do that. But it's not the case. We don't have this generic algorithm in the standard. And the reason is that it would make all the other, if we implemented all the other views using this, they will all have redundant members that they don't need, and it would make them bigger for no reason. And also, imagine what it would be like to call this generic algorithm. You would need to pass it 2 ints and a bool, and as you know, this always confuses callers about the order of the arguments and so on. So that was another small reason it wasn't added. Since we don't have named arguments yet, that would help there. However, you can easily implement a somewhat generic version, which I called windowed here, by combining slide and stride. now supporting whether the last range should be partial or not is left as an exercise for the viewer. The last windowing adapter we'll look at is called chunkby. So again, this chunks the range to different subsequences, but this time not of a fixed size, but it gets a predicate which it applies to decide when to cut the range, or where to split, basically. So this is a binary predicate, which is applied to every pair of elements, of adjacent elements. And when it returns false, then the chunk is split. Okay, so in this example, if we pass less equal, we get all the monotonically increasing subsequences of the source range. Now, if you've used range v3, then note that it had an adapter called groupby, which has somewhat different semantics. So this is, in fact, is now deprecated, so don't use that. Range v3 now also has chunkby, the same as the standard. All right, so let's go back to writing our calendar. So as I said, we had a list of dates and we want to split them by month. So we use chunkby along with a predicate which checks if two dates are of the same month. Otherwise, it will chunk it at that spot. So if we had this list of dates, we go from this to that, a range of ranges of each month. All right. So we mentioned that a certain type of views is views which generate those elements on the fly, and we have such a new adapter in C++23, and this is STD Generator. Now, I'm not going to delve deep today into coroutines and stuff like that. I'm just going to talk about the ranges aspect of generator. There are plenty of talks about coroutines, which I'm sure will do a better job than me covering the coroutine aspects. So this is a classic Fibonacci example of using STD Generator to generate the Fibonacci sequence. So pretty straightforward. We use co-yield to generate values out, and then we can iterate over this sequence, and I guess you all know what this program returns. Anyone wants to guess? Okay, that's 42, but yeah. Now, generators can be customized on 3 types. So each generator has what's called a ref, v, and allocator. There's also a PMR version, supporting polymorphic allocator. Now, what exactly those types mean? They decide what is the value type, reference type, and yielded type of the generator. So as you can see, is void means whether it is the default or not. So by default, the reference type of the generator is an R value, meaning it's, when you iterate it, you simply move out the elements. And the yielded value is the value that you pass to co-yield, basically. So most of the time you will just, maybe I'll return to this example. Most of the time you'll just pass a simple type like int here and use it. It will just work. If you have more, like, for example, generic code or stuff like that, you will probably need to look at those definitions. And you can see this this paper for more details about why it was designed this way. So if you want to yield a sequence, so you can take a range and yield all the elements from this sequence. Instead of iterating and calling yield repeatedly, you have this utility adapter called elements of, and what it does, it generates the elements of this vector in this case. This is also very useful if you have a recursive generator. So a generator which calls itself recursively, like this visit function. So what it does, if you yield the elements of a generator, it works the same as in the previous example. It generates all its elements one by one. So to me, I think this is a very elegant implementation of in-order binary tree traversal. I didn't write it, it's from the paper of, that introduces generator, basically. But I think it looks very nice. Yeah, another useful thing we can do with generators is using them to implement new adapters. So I'm not sure, Chris DeBella has a talk. Actually, it took him 2 talks to describe how to implement your own adapters. Using generators makes it much more easy, even though it has its cons. But in this example, I'm implementing the Concat View, which concatenates a list of ranges to one range, basically. And what I do is yield the elements of the first sequence, and then call the adapter recursively to yield all the other sequences. All right, and because of the properties of elements of, it works. It simply works. All right. Yeah, so I've talked about the cons of implementing it this way. Now, of course, it means you're using coroutines, which are probably more expensive than what would be if you would implement it properly. And also, there is generator is an input sequence. So that means it's single pass, and it might limit the usage of it. But for the sake of this talk, it worked for me, and I'll use Concat in a bit. So, by the way, Concat was proposed for C++23, but didn't bake it in, so I had to use generator to get it. Yeah, and this is how you would use Concat. Notice that you can concatenate different kinds of ranges, and the result will only be one range. Now, if you read the abstract for this talk, I talked about conceptual changes. So let's talk a bit about this, what concept has changed in C++23. Now, as you recall, we mentioned that a view is a lightweight range. But how it is defined in the standard. Now, before that, let's look at that generator. I passed it head and tail and all the ranges by value. So now it holds all those ranges. So basically it holds its elements. Now, is this a view? But by what we discussed before, not really. Now, this is the definition of view from the first paper proposing ranges from the standard library. And as you can see, the syntax is a bit different from what we have now. This was before concepts were finalized. So let's look at the next edition of this in a different paper. So what it says is that view is a range, of course. It is semi-regular, as you recall. It means that it is default constructible and copyable. And it satisfies this enable view concept. What enable view does is detect if the range has shallow constness. So shallow constness means that when an object is const, the elements are not have to be const. So you can change the elements even if the object itself is const. Think, for example, about reference wrapper, right? Even if the reference wrapper is const, you can still change its value. Or a const pointer, which not points to const value. There are many examples. And so it was, the thought was that if we want view to be, to have reference semantics, or to not own its elements, we can detect that whether it, by checking whether it has shallow constness or not. So that was, again, the first definition. But then there was a series of papers that were written before C++20 was finalized that relaxed this definition to support more types to be views. The first one was, just a second, I didn't skip one slide. All right. So the first one was move-only views. As the name suggests, it supports views which are move-only and not copyable. So it dropped the semi-regular requirement for just having default initializable and movable instead of copyable. Yeah. The rest was still the same. An example of a move-only view is a view over an input stream, which is usually not copyable. The next paper suggested that what we described, where we try to detect shallow constness and decide by that whether or not a type is a view or not, is not good because it has many false positives, types which have shallow constness but are not views. So this was dropped, and instead types were required to specialize this enable view trait to basically opt in to being a view or not. The next paper said, why do we really need views to be default constructible? It doesn't really add any value. And we can think of examples for views which we wouldn't want to be default constructible and would be useful, so I simply dropped that requirement. And then, yeah. Sorry, I forgot to talk about one element here is the fact that we want the operations to be cheap. Okay, so copying or moving, if it is not copyable, we want them to have constant time as well as destruction. Okay, because when we pass the view around, we either copy or move it and destruct it eventually, and we want all this to be cheap or constant time. And that's what all the comments there said. Now let's look at this code example. We get a vector from a function, so this is an R-value vector, and then we try to pass it to view adapters. that code doesn't compile in C++20. Why not? Because where would we put this temporary vector? We can't put it inside the view, because then the view would have all those elements and it would need to copy them or do something with them or destruct them eventually, and all those operations wouldn't be constant time. So what we had to do in C++20 was to put it in an L value, basically give it a name, and then the views could simply reference this L value instead of owning it. But what would happen if we did have this owning view? So this is a view which holds its underlying range by value. We move the underlying range inside. We disable copying, and we have a default move operations. So we have constant time move. The only problem is that we don't have constant time destruction, because we eventually need to destruct the range. But looking at this code example, if we would wrap get ints with an owning view, actually the performance of this whole snippet of code didn't change at all. We constructed a vector in get ints, we moved it inside owning view, and after doing all the transformation, we destruct it. So the same as we did before when it was named. So perhaps other than one or two moves here and there, the performance is the same. So there's really not a good reason to disallow it. And in fact, this is the main conceptual change of C++23, is that now you can pass an R value container to a range, to a view adapter, sorry, and it will wrap it in an owning view. And the way it is formalized in the standard, I'm not sure you can read those comments, but as you can see, it's a pretty long description to say that basically we expect the view to not make the performance worse. So if we construct a number of ranges, we don't want it to destruct more than what we constructed, basically. Same as for move operations and so on. So this is now the definition of view. This was actually reported as a defect report for C++20. So now the code we've seen in the first example compiles even when you're running with C++20, assuming your compiler supports that change. And going back to Concat, now Concat also is a view because it is move only and destruct its element once, basically. Cool. Now the last thing I want to cover before we go back to building the calendar is this addition to C++23 that allows you to make your own adapters composable, the same as the standard adapters are. So I'll explain more in a bit. This change also enables the standard committee to not have to introduce new adapters urgently, because users can always easily, more or less, implement their own adapters and make them composable the same as the standard ones. So for that, we need to see the definition of what is an adapter, basically. So a range adapter is an object which you can pass range as well as optionally other arguments to, and get back another range. Now you can either, as I said, pass the range as well as the other arguments on the same call, or you can just pass the arguments and get back a function object that you can then call with the range. Or usually what we would do is you would pipe the range into this resulting object, as you can see on the left line. Okay, if you think about views transform, for example, you can either call view transform range comma function, or call transform of a function and then apply that to the range. So the object that you got from calling adapter over the args without the range, this is what is called a range adapter closure object. So basically it's any object you can either call with a range or pipe a range into. So as I said, this is the result of transform of a function, or for reverse, for example, which doesn't have any additional arguments besides the range, this is simply the reverse object. And closures also have this property that you can compose more and more closures for a complete pipeline, and the result of composing two closures is itself a closure. So you can, this has this associativity basically. So in this, for example, I can combine reverse and transform, and the result of this reverse transform adapter is itself a closure, and I can pipe into that. So that was also in C++20. This is not something new. However, if I had a more complex adapter, then the result of this adapter is not itself a closure. And so I trying to pipe some range into that wouldn't compile. So how do I make this work? So in C++23 we get this utility object called range adapter closure that if you inherit from it, for example, by defining this function object, then your object is a closure and you can pipe into that. But of course, we don't want to go back to the days where we had to define function objects instead of lambdas. I'm sure you all still have scars from those pre-C++11 days. And so we do want our lambda to be pipeable as well. And for that, we can define this closure helper. So this object wraps some callable. It is derived from range adapter closure, and so it is pipeable. And it simply forwards the arguments when called to the wrapped function. So if I provide a lambda into this callable, into this object, then I get back a closure, and I can use the pipe and everything is good. Notice that I used CTAD here, the constructor template argument deduction, to deduce the type of the closure on line 15. Okay. So this is a closure. Sorry. So again, in this example, I'm not taking any additional arguments besides the range. So again, this is the property of a closure. If I did take additional arguments, like in this example where I also get a function, then I need to have an adapter, not a closure. And I can define a similar helper to this end, which I call adapter. And again, it wraps some callable. And when called, it first checks whether it can invoke the callable directly. So this would be the case if we call that with a range as well as all the other arguments. Otherwise, if we just pass the other arguments, it creates a closure and gives it back to us, and then we can pipe to this closure. Before I go on, just a note that those helpers, a closure and adapter, are not part of the standard, only the base class range adapter closure. And that's because the Barry Revzin, who proposed this change, wasn't sure those are the most, this is the best way to implement them, basically. But it's possible that they will be standardized in one of the following standards. So basically, you can, what I did was just copy pasting it from this paper, introducing them, and put it in some header, and then use it as if they were standard. All right, so we can finally go back to writing the calendar. So as you recall, we stopped with having a list of all the months. And now we lay out each month, or deciding how it would be printed. Now, to do this, we use concat. So we concatenate three things. First, some title, which will simply be the name of the month, followed by all the weeks of this month, formatted as we'll see soon. And then I'm just padding it with some empty weeks in case I have too few weeks in this month. I do this just to keep all the months aligned on the same line. Views repeat, which I use here on line 37, is also a C++23 edition, just repeating some value for a given number of times. So the month title is, I use STD format with the chrono support to get the month's name, as I said. This is center aligned to width 22. Then I split the month using chunk by 2 weeks, because I want each week on its own line. Note that the standard doesn't have a function to get the week number or something like that from a date, so I have this helper start of week to do that. And finally, to format the weeks themselves, this code is a bit involved, but basically it just takes the first week and right align it, and left align all the other weeks. And yeah, as you can see, this lambda is a closure, so I can pipe it on line 36 here. I can pipe my range of weeks into that. That's where I use closure. Now, this format is string helper prints the given range as a string, which this range doesn't have to be a string itself. It can be any range of characters, basically. And we'll we will go back to that helper later on, hopefully if time allows. All right, so to recap, we had this list of months, and then we call it month, and we get this range. So again, we have the month title, followed by the weeks, where the first week is right aligned, and optionally padded with empty weeks. Questions? All right, now we would like to print each 3 months side by side. So first, we use chunk to split the month to chunks of 3, of size 3. All right, and let's think about what we need to do next. So again, to tile all the months line by line, we need to take all the titles, which are the first elements of each month, so January, February, March, and concatenate them in a single line. Then we want the first weeks of each month, which are the second elements from each range, and concatenate them, and so on and so forth. So this operation of taking all the first elements and then all the second elements and doing something with them is called zipping. And C++23 also supports the zip adapters, which we will see shortly. If you've ever used Python, I'm sure you ran into this. So let's look at a few simple examples. This is, again, a classic example. We have a list of students and a list of grades, and we want to pair a student to its grade and print them together. So we zip the names with the grades. This will give us a list of tuples of the name and the grade. So this will be the output. Many times we want to do some more processing over those tuples. And for that we have zip transform, which gets a callable and calls it upon with each tuple basically, and it destructs the tuple for you, so you don't have to use toTie or something like that. All right, so in this example it calls this lambda with name and grade of each student. Yeah. So the properties of the resulting range, which we get from zip, is that its value type and reference type are themselves tuples. The value type is a tuple of all the value types of the input ranges, and reference type is a tuple of the reference types of the source ranges. Note that itself, the reference type is not a reference. It is a tuple, right? So this can be a bit confusing there. But it does have reference semantics. So by being a tuple of references, it's not actually a value in itself. Those reference semantics enable us something like this, where we sort the list of names by the list of grades. So we sort the names in descending order by the grade. Though this kind of stuff is very useful if you use the struct of arrays frameworks or something like that, where you have all your data spread out in different sequences, and then you want to do some operation of all of them together. So to support all the different concepts of ranges, C++23 also had to change tuple a bit, tuple and pair actually, to keep them compatible. And so we got more tuple assignment operators and more constructors, as if that list wasn't long enough. But yeah, you can, again, read the different papers. I have some sources in the end if you want to truly understand those changes. But again, this is a case of Herb Sauer likes to say that we add stuff to the standard to make the user code more simple. So we can simplify C++ by adding stuff to it, and I think this is a good example for that. There are more views that generate tuples in C++ 23. Views adjacent is like split only for compile time size. So we pass this size 3 in this case as a template parameter. Notice that we also use another C++ 23 adapter enumerate here, which gives you a pair of the index and the element of each, the index and the value, sorry, of each element. Again, very, very useful if you want to, for example, call some legacy code, which usually expects an index. The version of adjacent which has size 2 is called pairwise, which is just an alias. And lastly, another view of which generates tuples is Cartesian product. This generates basically all the possible combinations of elements from the given ranges. All right, so let's go back to the calendar. So as I said, we want to zip the months. So take all the first elements and concatenate them, followed by the seconds and so on. So we do this in this function. We use zip transform and passing it the 3 ranges, or the 3 ranges. So each month is itself a range. Now, in Eric's implementation, this was called, he called it transpose. So basically you take the row of months and transpose them to columns of months. And for that, he implemented a new adapter, which he called transpose. Basically, this is the runtime version of zip, the same way that slide is the runtime version of adjacent. But I guess, so his version enables the user to provide what is the required number of months to print side by side. I'm not sure how useful that would be. I mean, usually we would want either 3 or 4. So we can simply use this version. Also, I want to show you zip transform, so I had to use that. Yeah. All right, so again, we stopped at this point where we chunked the month by 3, and we got a list of chunks of 3 months each. And after calling transpose, now we get all the names concatenated, the first weeks, the second weeks, and so on. So it almost looks as what we want. What is left is simply to join all the chunks. So we use the join adapter from C++ 20. Then we have the list of all the lines, and we concatenate them to a single line by using join with, which puts the given element in between every two elements and concatenates the whole sequence. This is also a C++23 addition. All right, so this pretty much looks like what we wanted to achieve, or actually it is what we wanted to achieve. Now remember we had this formatted string helper, which I didn't cover yet. Now the reason I needed it is because not all the standard libraries support formatting ranges. In fact, only Clang supports it currently. And not that all what I've shown you is supported already in all the standards, it's just that it is easier to implement. So basically for implementing all the adapters, I just copy-pasted the reference implementation or something like that. But for something like formatting ranges, it's much harder. So, and as I said, all the examples compile. If you have the slides, you can use Control-Shift-Click to click on an example and open it in Godbolt. Okay. Now I probably won't be able to go back. Yeah, let's close it. Okay. All right. So again, I wanted to format my range as a string, and I didn't have the standard library for that, so I simply convert the range to a string and then print that as I could do in C++20. And this is easier to do with this C++23 edition of the to adapter. So to takes a range and returns a container, basically. In this example, we take the iota view and convert it to a vector of ints. So it simply copies or moves all the elements from the input range into the container. All right. You can also pass an allocator if that's your thing. If you're from Bloomberg or something like that. You can also deduce the type. Okay, so if here we had to provide the types explicitly, we can let to deduce the types for us. So we will deduce them according to the value type of the source range. Now, to enable this, all the standard containers got new constructors, which receive this from range tag type as a first argument. If you recall, we didn't have, so for example, vector didn't have a constructor accepting a range. It only had one that accepted 2 iterators. So now we have this constructor. So we can call it directly. And actually the way that 2 is defined is like this. First, when it gets a range and a list of arguments, it tries to pass them directly into a container of the requested type. If this fails to compile, it searches for a constructor taking this from range tag type. If that fails, it calls a constructor accepting an iterator in a Sentinel, not a pair of iterators. And if that fails, it resolves to just reserving the required number of elements if the container has this reserve function, and pushing back the elements one by one. Now, if we give it a nested range or a range of ranges, then it calls itself recursively to do the same operation. So why, in fact, do we need this tag type from range? So let's, if you'll think about in this example, if you pass a list to a vector, you won't get a vector of ints, you will get a vector of lists of size 1. Right? This calls the initializer list constructor with a size of 1, and this is the result. So if we wanted to convert from a range to another range, we need to call another constructor, and this is the from range constructor. And now we get a vector of ints with the same elements as the list. So 2, as any adapter, is composable. We can pipe into it. Notice that you must have the empty parentheses here in the end. You will get nasty errors otherwise, if you forget them. Yeah, this is one problem we still didn't fix. You can convert, so if you start from a range of ints, for example, you can convert them to a vector of another type of elements, assuming the types themselves are convertible. Another useful thing you can do is to use zip to basically construct a map using a list of keys and a list of values. Okay, so here the names will be the keys and grades will be the values in the resulting unordered map. As I said, 2 supports nested ranges, so you can easily convert a list of forward lists to a vector of a deck or whatever you want. And it also supports not just standard types, but user-defined types. As we described the algorithm, so assuming you have one of the constructors it tries to call, it will work. Together with the added constructors, we also got more convenient functions to insert ranges into containers. So insert, append, assign replaces what was before instead of appending and so on. Okay, so to implement format as string, as I said, I check using this macro if format ranges is supported. Otherwise, I convert my range to a string using toString and prints that. All right, so let's take a risk and do a live demo. All right, so I have here VS Code with all the code. I don't need to read it, just know it's there. Basically, we passed almost all of the code except for the main logic, which gets the arguments and so on, and passes them to the adapters we've seen. And this code is also on Godbolt. I have a link at the end if you want to check it out, or on my GitHub. All right, so let's run it. First, we'll run it to generate the calendar for this year. Okay. And then, as I said, I also support the infinite range of all the years starting from this year and never stops. If you ask Matthew, it might think otherwise, but yeah. So we have a few minutes left. So I thought to cover one more C++23 addition, which I didn't use in the calendar code, but I think it is very useful generally. Sorry. And those are the folding algorithms. So what are they? So this, in fact, is a family of algorithms. Sorry. If you remember, this ties back to one of the first code snippets we've seen, where we try to call accumulate with a range, and as you recall, C++20 didn't have a rangified version of accumulate. So now we got it. This is called, but with a different name. This is called, sorry, fold left. And so what it does, it gets a range, an initial value, and a function, and it calls the function with the initial value, and to begin with, it calls it with the first element, then the result of that is passed to the next invocation, along with the second element, and so on and so forth. So let's see how we use it. If we pass it STD plus, we get accumulate back. So we get the sum of the elements of the vector in this case. But we can also pass other callables like multiplies, but not only math functions, okay? The main reason they changed the name was that accumulate was too tied to being addition or mathematical, and actually there's no reason to just limit it to math functions. It is very useful in a lot of cases. And so fold left doesn't by default have addition or something like that. You need to pass the callable explicitly. In this example, not very easy to understand what it does, but basically it just enables a nice way to format ranges. For example, here I used it to simply generate but this is not very readable. Yeah, so I simply used it to print the definition of fold left. Just a small toy example. All right, so this just to show usage of not just math. Now, a very good usage for fold left is to implement another algorithm, sorry. So in this example, we can implement count if, which counts the number of elements in a range that satisfy some predicate by using fold left. So we start with the count, the initial count is 0, and then we call the predicate, and whenever it returns true, we increment the accumulator, sorry. Otherwise, we stay with the same accumulator. So in the end, we'll get how many elements return true on this predicate return true for. Okay, you can do many algorithms this way. Now we've seen fold left. There is also fold right, which passes the initial value as the right argument to the function, and go along with the last. So we start from the last element. It goes in a reverse order, basically, over the sequence. And this is done to satisfy some nice equivalence relations. And so I couldn't think of a useful thing to do with the fold right. I'm not sure if you know. Tell me. Just can use it to implement the definition the same as I did before. Yeah, you can check it out later on Cobalt. Now, we've talked about implementing algorithms, so let's see what if we try to implement the minimum algorithm, how would we do it? So what would be the initial value we wanted to, we should pass to fold left to implement min? Anyone wants to guess? Okay, so our predicate is simply comparing the current minimum to the next element. Yeah? Suggestion? Maximum? Oh. Yeah, but remember we don't want to work on numbers. It can be any range. Sorry? Yeah, exactly. We can just pass the first element and it will be the maximum if no one, the minimum, sorry, if no other element is less than this. But this is a bit problematic because first we have one invocation which simply compares first to itself. So we use a bit, this is redundant. And second, this makes this code works only on forward ranges. So on input ranges, we're not allowed to call begin twice because input ranges are single pass. So here we call begin here and as well as inside fold left. So this is a bit problematic. And so for this, we get another algorithm in the standard called fold left first, which simply do the same thing. The first call to the predicate or the function object is on the first two elements, and then it continues from there. So it doesn't have those problems we discussed before. The only thing is that since it calls on the first two elements, it uses the first element, the input range can't be empty. And so for that, it returns an optional. If the input range was empty, it will return an empty optional. And so if you want the value, you should dereference this optional. Now, of course, this will be undefined behavior if the range was empty and you got an empty optional, but this is actually how the standard minimum is defined. It has undefined behavior for empty ranges, so to have a conformant implementation, we do that as well. But generally, you should check your optionals before dereferencing them. Now, remember this law of useful return from Stepanov. Now, you could ask, okay, why don't we return from fold left the end iterator as well as the result? But that would make each calling code look something like this. So 99% of the times we're only interested in the result, not in the end iterator, when we would have to discard it on each call. So it's not very nice. So fold left does return only the result, but you have fold left with iter that returns you the iterator as well, if that's what you need. And to conclude, this is the whole family of folds in the standard. And we're reaching the end of our talk, so I have a few resources here. There's, as I said, my implementation of calendar using C++23 on Cobalt. There's Eric's implementation on range v3. Again, I highly recommend Eric's talk from 2015. If you're interested more about formatting ranges, Barry Revzin gave a talk at last TPPCon, which I highly recommend. And also to access all the papers for all the different adapters added to C++23 and also what is planned for future standards, you can check out this link at the last line. And with that, I thank you all for coming.